Hi, my name is Mohammad Yusuf Ali. I'm an URAS postdoctoral fellow at FDA. In this presentation, I'll demonstrate how to incorporate historical control data into the detection of treatment-related effect in toxicological studies. So this presentation reflects the views of the author and should not be construed to represent FDA's view or policies. Any example or sample analysis in this presentation are for illustrative purpose only. So non-clinical toxicological studies are done in a small group. For the rodent, the group size normally 10 parsecs per group. For the dog and monkey, is group size is even smaller. It's 3 to 6 per group parsec. So since the group size is small, it is challenging to interpret the results when you compare control group and treatment group. SEND stands for Standard for Exchange of Non-Clinical Data. Is SEND developed by CDISC, provides a structured electronic format for organizing and exchanging non-clinical study data between company, CRO, and health authorities. In December 2014, the FDA finalized a binding guidance requiring certain clinical and non-clinical studies be submitted with standardized electronic data. So that creates an opportunity to um, extract historical control information and also analyze historical control data. So there is an R package called Sendiger. The package developed and maintained by BayesianTox in collaboration with Fuse Non-Clinical Topics Working Group. So Sendiger package contains a set of functions to extract and filter data for control animals from database. And historical incidence rate can be extracted using Sendiger package. The good news is the package also include a Arshani app. So Arshani app can be used to get the incidence rate or historical control information. So how we integrate historical control in animal information into our current study? We chose to work with Bayesian method. So there are many clinical trial study that uses Bayesian method to, like in case like pediatrics, rare case, and medical device situation. So when it is quite challenging to add more patient in the group, so that's when it's quite useful to use historical control information in current study. So we use Bayesian method, and since when we treat a animal with placebo or treatment, so there is two possible outcome: a response or no response. So binomial distribution is used in the event of two possible outcomes. So we we chose beta binomial distribution for our prior uh, distribution. Uh, so we can represent prior expectation with a beta distribution. Beta, this beta represents beta distribution, and the parameter is alpha and beta. So the mean of the beta distribution is alpha divided by alpha plus beta. So the posterior distribution became alpha plus x and beta plus n minus x. So n is a number of the total number of animal in a group, and x is the total response of the total number of response in a group. So we can say that alpha plus number of the responded, number of that responded, the number, and beta plus number that not responded. So see, the total n is the total number in a group, x is the responded, so n minus x is not responded. So alpha plus responded, beta plus not responded. So I mentioned earlier the Sendiger Shiny app. So where you can filter like parallel study design. You can filter the date, study design, order of administration, species, strain, and sex, and then uh, it extract the control animal information from the database, and then you can choose like which organ you are looking for. So it's right now it's selected is kidney. So we're looking for kidney in the rat Sprague-Dawley, that's male administered oral garbage. So in here normal was 40%, basophilic tubules 23.33%, and nephropathy was 20%, and so on. So we can get this historical information from using the Syndiger package or app. So let's say the basophilic tubules that we shown here 23.33, that's for our calculation, let's say that's 25. So that's 25, and the mean of a beta distribution alpha divided alpha plus beta is 20.25. So since the beta distribution with we can construct a beta distribution with this 25% mean event rate by setting the mean of beta distribution alpha divided alpha plus beta equal 0.25. Now, how much weight we want to placed on the prior information, also known as effective sample size, ESS, and ESS is equal to alpha plus beta. So we can set this alpha divided alpha plus beta in different and get the 0.25 in different using the different number. So if we use 1 by 4, that's 0.25, 2.5 by 10, that's 0.25, 5 by 20, that's 0.25, 10 by 40, that's 0.5, 0.25, 25 by 100, that 0.25, 250 by 1000, that 0.25. So there are many ways you can make set alpha divided alpha plus beta equal 0.25. So if we further break down this number, we can see that we can choose alpha and beta in a different way and still can get this number equal 0.25. So there are if we need to select the ESS alpha plus beta. So alpha plus beta could be like 4, 10, 20, 40, 100, 1000 and more. So how we choose which value we will use for our model or our app. So when you choose a bigger number, ESS 1000, so this distribution for ESS 1000. So when you choose a bigger number, the variance of the distribution are less, and when you choose a smaller number, ESS, a smaller number, the variance of the distribution is high. So then it comes like if you want to place a high weight on prior information, you choose a higher number. If you want to put a less weight on the prior information, you choose a small number. For this experiment, we choose uh, ESS, effective sample size ESS 10 for control group. So ESS is alpha plus beta. So why we choose 10? So we get this incidence rate for for the basophilic tubules, the incidence rate is 25%. So we get this incidence rate using only previous studies. So that's why we want to put less weight on the prior information. That's why we choose a smaller number. The informative beta binomial priors. So we started our example with mean 25%, ESS 10. So that and since we chose ESS 10, that mean alpha 2.5 and beta 7.5. For our treatment arm, since we don't know anything about the historical treatment arm, so we chose ESS 1 because we want to place a less weight on the historical treatment arm. So we choose 1, and this is by default the same as the control. Because we don't know anything, we chose a small ESS, so that will affect less. So the prior beta for treatment arm is 0.25 and 0.75. So this is our new study. In the control group, there is 3 animal. In the treatment group, there is also 3 animal. In the control group, let's say there is 1 animal that responded, and the incidence basophilic tubules. And in the treatment group, there are 2 animals show basophilic tubules. So in the control group, 1 responded out of 3. In the treatment group, 2 responded out of 3. So our beta alpha plus x and beta plus n minus x. So in the control group, alpha 2.5 and number of animals that responded 1, and beta 7.5 number of animals that not responded is 3.1, the 2. So beta 3.5 and 9.5. In the treatment group, beta 2.5 plus number of animals that responded, the 2, and 0.75 plus 3. Number of animals that not responded. So total number of animal minus number of animals that responded equal number of animals that not responded 1. And then we simulate the uh, simulate this simulate this number, and we find that mean of the treatment mean is higher than the control mean is 86% time. So if you follow this link, you will find this. You can access this Shiny app. So in in our example, the control group size was 3. So for any different number, you can type it here, or you can use the up and down arrow button. So control size 3, the incidence in control group was 1. So when you change this number here, control group size, this will update the range in here in the incidence in control group. So just 3. So now we can change the how many incidents in the control group. So treatment group, there was 3, and incidence in the treatment group was 2. Now historical control incidence rate that we get from our uh, historical control information, like using the Sendiger package or Shiny app, we get this value from there. Now effective sample size for control, ESS is it was equal to alpha plus beta. So if you want to put higher weight on the historical control information, like prior in the prior information, then you choose a large number. If you want to put a less weight, then you choose a smaller number. So and then click update, so that will generate the table. So this is the control mean and treatment mean, and this is the probability. So in our study, there was a group size 3, incidence 1, group size 3 in the treatment group, incidence 2 in the treatment group. So what it means that the probability of treatment mean higher than control mean. So this treatment mean is higher than control mean is 0.86 when the historical control incidence rate is 0.25. Now if we change this 0.25 to 4, that means these incidents are very frequent in the control group. So right now it's 0.86, so we update. It changes the control mean and treatment mean, and the now probability is decreased. So that's mean the now treatment mean is higher than control mean, also decreased. So now treatment mean higher than control mean, now 0.79. Now if let's say we have an incidence that are very rare in the control group, So we update. So now control mean is 0.15, 0.12, and treatment mean 0.51. Now probability is 0.95. That's mean now treatment mean is higher than control mean is 0.95. So you can see that when historical control incidence rate are higher, this probability that treatment mean is higher than control mean is less. And then when the incidence in the control historical control incidence rate when are low, like 0.05, the probability that treatment mean is higher than control mean increases. So this is very simple app. So you can follow this link and use this app. So there is another row frequentist mean. So for out of three, one incidence, that's 0.33, and two incidents in the treatment group out of three, so that 0.67. So whether if we change the historical control incidence rate, the frequentist mean does not change because it does not take consideration of the historical control incidence rate in calculation. So this is how we can incorporate historical control incidence rate in our current study if the control group size is small. So it also help to interpret the result, like it easy to say like this is the probability that treatment mean is higher than the control mean. In the future we have planned to build a logistic segregation to add more data points. Like if we have a study like low control, low dose, medium dose, high dose. In that case, we cannot use these current models, so we need to build another model. And in that case, we need to, in more complex case like this one, we need to rely on Markov chain Monte Carlo draw sample from posterior, and we have planned to improve user interface of the app and add some visualization if possible. So I'd like to thank you, my mentor Kevin Snyder, for for giving the opportunity to work on this project and helping me to helping in these projects. And I also like to thank James Travis, the statistician at the Cedar. He helped us to understand the Bayesian model. Uh, and any question related to statistics he answer. So I'd like to thank him. And this project was supported by an appointment to the research fellowship program at the immediate office in the Cedar, US Food and Drug Administration, administered by ORISE, an intelligence agreement between US Department of Energy and FDA. So I'll thank FDA, US Department of Energy, and ORISE. With that, and I would like to thank you everyone for watching, for your attention.